Hello, everyone, and welcome to day 2 of the 2022 playoffs for the AI in 5G challenge. Just a friendly reminder for those who were not here yesterday, the presentation should be around 10 minutes long and it will be followed by a 5-minute Q&A session. Without further ado, I'd like to kick off the presentations for the first problem statement, federated traffic prediction for 5G and beyond. Can I welcome Team Euclid?
Hello, everyone. Can you hear me?
Yes, we can.
Okay. So may I share my screen?
Yes.
Okay. So hello, everyone. My name is Vasilis Perifanis, and I'm a PhD student at Demokritos University of Thrace, Greece. Today, I will present you a recent work, Federated Learning for 5G base station traffic forecasting, which is a joint work with Nikolos Pavlidis, Aris Koutsiamanis, and Professor Pavlos Efremidis. So in this challenge, we are interested in traffic prediction, which is a key component in 5G infrastructures and enables efficient and intelligent planning and management. Several recent works focus on the application of deep learning models, such as multilayer perceptrons and recurrent and convolutional neural networks. These models have been shown to overcome traditional approaches such as ARIMA-based models. However, traditional centralized machine learning requires the transmission of private data to a third party, which violates regulations and laws such as the GDPR, or business confidentiality issues prevent organizations to share their data. A solution to this problem is to employ a collaborative learning approach, which enables a model's training without requiring data transmission. So our challenge here is to build a federated model architecture, given as input the 10 past observations per base station, where each observation contains 11 measurements, such as the uplink and transport, downlink transport block sizes, and our goal is to predict the values of 5 measurements for the next time step. To this end, we are given access to a dataset comprises 3 base stations in the metropolitan area of Barcelona, Spain. Elborn contains samples from 7 days, Les Corts contains observations from 12 days, and finally Pavlsek contains samples for about a month. As you can observe in these 3 figures, which depicts the downlink transport block sizes per base station, each base station holds its own unique patterns. The blue lines correspond to the training set, the orange lines to the validation set, and the green lines to the testing set per base station. But what is federated learning and how it works? First of all, we have a pre-processing stage in which the base station locally transforms their data and make them ready to be fed into a machine learning algorithm. Then the federated learning follows a unique training logic. At its core, there is a central server who acts as the coordinator of the training process. At every federated round, the central server transmits the global model parameters to the participants, who perform local training iterations using the global model along with their local training observations. After local training, they transmit back the updated local models to the server, who performs an aggregation step to form the new global parameters. This process continues until model convergence. A unique characteristic of federated learning is that we do not operate on the assumption of independent and identically distributed data. In our problem, we observe that we have a mixed type of skews, and specifically, we have feature and target distribution skew, which means that each base station holds its own unique patterns. We also have quantity skew, which means that our base stations hold a different number of observations. And finally, we have a temporal skew, which means that our measurements are collected during different time steps. To provide the solution to this task, we implemented from scratch a federated learning framework in a simulated environment and considered 5 different model architectures: a multilayer perceptron, a recurrent neural network, a long short-term memory network, a gated recurrent unit, and a 3-dimensional convolutional neural network. This model has been given from the organizers of the challenge. In addition, we consider several aggregation algorithms. Some of them, such as the FedProx and FedNova, are specifically designed to handle the non-IID data issue. To evaluate their approach, we use the normalized root mean squared error regarding the uplink and downlink measurements, and you also measure the energy consumption and the carbon footprint. We begin our experimental study by assessing the influence of pre-processing to the final predictions. The first thing we noticed is that all base stations contain values that fall far away from their mean and can be considered as outliers. So we compare our learning models with respect to the normalized root mean square error by considering a training process using the raw data and a training process with an outlier handling technique. With the raw data, for example, in the long short-term memory network, when we end up with a normalized root mean squared error of about 1.1. But with flooring and capping, which is an outlier handling technique, and specifically we give the model a minimum and maximum value, and these values that fall below the minimum and above the maximum of our specified values, they floored and capped to those values. Using this technique, we end up with a normalized root mean squared error of about 0.7. In addition, we measure the influence of global and local scaling. In local scaling, each base station locally transforms the local data using the local minimum and maximum, while in global scaling, we announce a global minimum and maximum. Here we observe that the global scaling approach leads to higher quality models. So we continue our experimental study using the flooring and capping technique for outliers handling and the global scaling. Here are our final results per federated model on the validation set, which is depicted with the blue bar, and on the testing set, which is depicted with the cyan bar. In all cases, we observe that all models tend to provide almost equivalent predictive accuracy, with the long short-term memory network and the gated recurrent unit performing the best. These models also lead to lower standard deviation, which means that they provide robustness against random initialization. In addition, we compared the models trained under the federated setting with their corresponding centralized counterparts. In all cases, we observe that the final normalized root mean squared error is almost equivalent in both settings, and in some cases, such as the long short-term memory network, the federated setting slightly outperforms the centralized model. Finally, we assess the influence of the aggregation algorithm to the final prediction. Here you use the long short-term memory network, and our baseline is the federated averaging algorithm. From FedProx onwards, these aggregators are specifically designed to handle the non-IID data issue. Here we observe that although these aggregators are specifically designed to handle such issues, they do not significantly outperform the federated averaging baseline. We attribute this behavior to the fact that these aggregators are designed with one type of skew in mind, but as I mentioned earlier, here we have a mixed type of skew. We have the feature, target, temporal, and quantity skew, and cannot significantly outperform the federated averaging baseline. Nevertheless, we observe that FedNova and FedProx actually leads to lower root mean squared error, and our final solution concerns the long short-term memory network along with the FedNova aggregator. Later, we observe that FedProx actually leads to better results. Finally, we measure the energy consumption per model in both the centralized and federated settings, and we observe that federated learning leads to lower energy consumption and subsequently to lower carbon footprint. Here is an example of our final predictions per base station regarding the downlink and uplink transport block sizes. And to begin with the Elborn and Publisec base stations, although our model follows the corresponding patterns, it misses some higher values. We attribute this behavior to the fact that our model is not specifically designed to handle such spikes, and also these values are relatively high. They are in terms of billions. In the future, we will try to focus on the model architecture to capture such behavior. In addition, in less courts, our model not only captures the pattern of this base station, but also our final predictions are almost equivalent to the ground truth. So in general, our federated model can provide high quality predictions. To sum up, during our experimental study, we observed that pre-processing hugely affects the forecasting error. Although this stage has been given much attention in the generalized context of machine learning, to the best of our knowledge, there has been limited conducting research on its influence to the federated setting. So we triggered the research community to focus on this stage, which can potentially solve at least some cases on the non-IID data issue. In general, we observed that models trained under the federated setting provide almost equivalent predictive accuracy to the centralized counterparts, but with federated learning, we minimize privacy concerns. We enable a dynamic execution environment. For example, we can retrain the model once per day or week or when data are available. And finally, we allow participants to perform local fine-tuning. In other words, after the generation of the global model, participants can perform additional local iterations to personalize the model. Finally, we observe that although some aggregators are specifically designed to handle the non-IID data issue, they do not significantly outperform the federated averaging baseline. So a future critical direction is to focus on models and aggregators that can handle temporal dynamics to provide higher quality predictions. Thank you very much for your attention. I would be happy to answer any of your questions.
Okay, thank you very much for the presentation. Can we start with Evan? Your question, please.
Thank you, Mia. Hello, Vasilis. Thank you for this nice presentation. Could you please give a little bit more idea about information about your architecture and what kind of hyperparameters did you tune? And
okay,
I am really wondering about the loss function that you use, because maybe you, by using an appropriate custom loss function, maybe you can handle the outliers in your predictions.
Yeah, that's true. If we use another loss function, we may handle the outliers. Here we considered, our final solution considers the long short memory network with, and the loss function is the mean squared error. We didn't attempt to use other loss functions since we want our models to generalize to provide generalization on the time series forecasting tasks. So we leave additional evaluation on the loss function specifically for the future.
Okay, thank you.
If you want to, I can tell you about the other hyperparameters such as the learning rate or whatever the epochs we used or the architecture of the long short-term memory. No.
Okay. Can we next have Tian? Is that it?
Hi, thank you so much for the chance, and that's a good presentation. I just have a quick question about your federated learning setting. So in your evaluations, did you use 3 clients?
Yes, our clients are the 3 base stations, Elborn, Lescourt, and Published. Yeah.
Okay, I got it. Thank you.
Yeah, and in our experimental study, we report the normalized root mean squared error on average. We consider all base stations and take the mean of the normalized root mean squared error.
Okay, got it. Thank you.
Are there any more questions from the judges? Okay, do we have any questions from the audience or competing teams? Thomas, please.
So in this case, you have indicated that you took the normalized root mean squares for like all the base like the stations that it means. In this case, you have 3 stations you are considering. In the case that you are considering like independent errors, what would you say about the performance of the models?
Let me go to this slide. Here are the predictions per base station. Here we do not report the normalized root mean squared error per base station, but as it can be easily observed here in less courts, the normalized root mean squared error is relatively low because our predictions, which are the orange lines, are almost equivalent to the ground truth. On Elborn and Pavlsek, the normalized root mean squared error were about 0.8 because it misses these higher values. These higher values, although it's about 1 billion, and our model cannot capture them.
Mm-hmm.
So yeah, in less courts, the normalized root mean squared error is about 0.3, and on the other cases is about 0.8.
Okay, and maybe the next one. I'm quite interested because for your solution, you also considered the energy consumption, and maybe can you elaborate more on the performance in terms of the energy gains, the trade-off between the accuracy of the models, how long you take to train, and maybe the energy consumption and your insights maybe that can help the community as well.
Yeah, here we, in all cases, all models provide almost equivalent energy consumption. For example, in the federated setting, the multilayer perceptron is 0.001, and the convolution neural network is about 0.002. So these models do not lead to high energy consumption because they require a limited number of epochs. The convergence is the final solution here, the final model which performs the best is given on about after 7 epochs, if I can recall. So the energy consumption is low. All models are environmental friendly, and for the future we may use a technique to actually measure the energy consumption, because here the energy consumption is made from approximations using a Python framework. I don't know if I answered your question here.
Yes. Thank you very much.
Okay, well, do we have any other questions? Okay, well, thank you very much, Team Euclid. Moving on, our next team is from SFY, but apparently the team member is feeling a little sick today, so we are going to move on to our next problem statement. Non-linear power amplifier behavior modeling to achieve higher energy efficiency in 5G RAN. Can I welcome MLAP, please?
Yeah, so let me try sharing my screen.
Yes.
Hope my screen is visible.
We can see your screen.
Yeah. Okay. Let me know when I can start.
You can start.
Yeah. Hi all, myself Sai Krishna from team MLAP, which also consists Ashok and Hari. We are a team belonging to Beyond 5G group of Samsung R&D Institute, Bangalore. I'm here to present our solution, nonlinear power amplifier behavior modeling to achieve higher efficiency in 5G RAM. In wireless communications, generally the information is first modulated at the transmitter and is transmitted over a wireless channel. The receiver receives the signal and demodulates it to reduce the information. But the wireless channel here introduces path loss, or in other words, it attenuates the signal. So we boost the signal before transmitting it using a power amplifier so that the receiver can receive the signal in spite of the path loss. Ideally, we expect the power amplifier to provide a linear gain of the input signal, whereas practical power amplifiers introduce nonlinearities, especially when operated at higher power. They also cause interchannel interference. A overview of what are the kind of nonlinearities that we might observe. Here, the red line is assuming like if we have a linear amplification, what should have been observed, and the blue corresponds to a realistic power amplifier data here. The bottom two are like AM, and AM, PM characteristics, which are pretty well known in time domain. In frequency domain, also the power amplifier actually, some power actually leaks into the adjacent channels, whereas ideally we want all the power to be within the in-band frequency. Also, you can observe like for the same input, there are multiple outputs. This could be because of the memory effect. That is, the past sample effect is being perceived in the, or is having some effect on the current sample's output as well. Now here, the problem is to accurately predict the output sequence of the power amplifier given the input sequence. The power amplifier, as we have already seen, might consist of nonlinear effect and also memory effect. So we can model the power amplifier by minimizing the loss between the actual and predicted power amplifier outputs, and then updating the model iteratively. I mean, this is a generic approach. What will this help with? I mean, this helps in understanding the nonlinearity that is introduced by the power amplifier, and that will eventually help us in building this nonlinearity compensating algorithms so that we can improve the efficiency of the wireless communication system. Now, in literature, power amplifiers are modeled majorly into three classes. Like one of them is assuming memory doesn't have any effect. They are called memoryless nonlinear models. And other approach is to assume that the memory is linearly affecting. Those are called nonlinear models with linear memory. And the last one is nonlinear models with nonlinear memory. Now, if we see the mathematical equation for each of these, it is like a linear combination of the input signal and its absolute term powers. And there is no memory component when we are talking about memoryless nonlinear models. Whereas when we move to linear memory, actually the mathematical equation of this is represented as shown in this equation, which if we closely observe actually represents the nonlinear model of a memoryless, but at various memory types presented by a m variable. So, but even these equations are with a lot of assumptions, but were able to actually predict the PA outputs very closely. So we know that these features, that these nonlinear functions will have a really good realization of the PA output. So inspired by these nonlinear terms, which are common across all the models of PA modeling a priori, we try to model our input structure based on the input sample, which is a complex number. So we took the real and imaginary part of it, and the absolute terms and their higher order powers. And then with few assumptions, we would have come up with this equations, mathematical equations. So there could be a bit more nonlinearity, which could be missing by just realizing this equation. So we tried to have another few hidden layers to learn more nonlinearity, if at all the data can provide us with. I mean, there is some function that can be learned. So that can be learned over the hidden layers with nonlinear activation functions across various of these nodes, where the output should be mapped with the output of the power amplifier, the real and imaginary part of the same. Now, similarly, extending this onto nonlinear models with linear memory, we can just say that for multiple current and past sequences, like the current sample is n, whereas the past samples are n-1 up to n-m. For each of them, we can have a separate subnetwork corresponding to this memoryless part, and then they are combined linearly to obtain a power amplifier output. But majority of the cases, like we have both nonlinearity introduced the power amplifier, and also there will be nonlinearity introduced because of the memory aspect as well. This is one of the most celebrated power amplifier conventional model for power amplifier modeling, known as memory polynomial, which takes nonlinear memory part also into picture. So instead of completely changing the architecture, we just took this architecture where we have separate subnetworks for each of the current and past M memory taps corresponding to this. So the input also, the inputs are also fed, inspired by the features that were being extracted here. And we had added this part of the network, which is completely fully connected to learn the effect of nonlinear memory a bit appropriately. And these are mapped to the output of the power amplifier. Now, there are various advantages of using such a network. One is like, since each of the sample, we are having a separate subnetwork to really understand the nonlinearity, we can actually change the number of nodes that we are using in the hidden layers associated with that particular memory tap alone, thereby giving more learning or more parameters to get the function more accurately for the current sample, and giving lower and lower priority as we go to the past samples. Also, this is comparatively less complex compared to general NN architectures, because we don't have multiple cross connections across the initial layers, where the number of elements that we need to work with will be much higher, but effectively capturing the required information. Also, like even the non-linear degree terms also can be adaptively changed for each sample because of having this subnetwork for current and past samples accurately. In the solution that we have proposed, we have used the nodes and other parameters of the network as shown here. The maximum order that we chose was 2, with the memory length to be 11. And the input nodes in hidden layer for current sample to be 9 and past samples to be 5. And the number of nodes in the hidden layer 2 for the current sample is 5, and the past samples to be 2 for all the cases. And then for this part, which we wanted to use to capture the memory effectively, are fully connected with 3 hidden layers, HL3, 4, and 5. Having 10, 20, and 10 nodes each respectively, which are then fed to the output layer, which actually predicts the real and imaginary part of the PA output. The activation functions we used for this network are leaky ReLU throughout. Now, during training phase, we have the network architecture. So we have the data set. So we took the training data set, we normalized the samples using the maximum absolute maximum of the absolute value of the input sequence across, and then across all the samples, and then we trained the network to minimize the loss function, that is the mean square error between the predicted PA output and the actual PA output. And during this was with using ADAM optimizer with a batch size of 200 over 3000 epochs. During testing phase, like we get the input sequence, then normalizing it using the normalizing factor that we found in the training phase, and then predict that predicted value is then multiplied with the normalizing factor found in the training phase to get the final output for the testing data sets. Now, for training, we had 1,83,964 samples. For testing, we had 4 different data sets. The first 2 data sets consisting of 40,000 samples each, and the last 2 data sets consisting of 65,536 samples each. In the first 2 data sets, the 40,000 samples again are divided into 2 sets of 20,000 samples with different average powers. And the metric the organizers have proposed to use to understand how effectively we can model the PA data are NMSC, which is the normalized mean square error in log term, and ACEPR. The ACEPR metric represents the error power of the model leaked into adjacent channels. Now, for comparison, we got the memory polynomial results with memory length 11 and maximum degree of 2, so that the comparison can be fair. And then these are for various data sets as mentioned before. As a summary, we can see on average, the proposed solution has a 6.84 dB improvement in NMSC and 7.26 dB improvement in ACEPR compared to conventional memory polynomial based approach. The complexity of the network, in summary, turns out to be around 1100 multiplications during per single inference. Also, the overall score for this problem statement was evaluated by giving 30% weightage to NMSC, 30% weightage to ACEPR, and 40% weightage to the complexity. I mean, in all the cases, the lowest the best. So with this, like the organizers have then evaluated our solution, and we were topping this solution with a score of 60.8, 100. After we submitted the solution, we further experimented to improve the solution. So we tried to change the activation function from leaky ReLU to TANH for the fully connected layer alone in the network. That is only these three hidden layers in the network. We changed the activation functions to TANH from leaky ReLU, and we observed a further improvement from whatever we proposed previously, 0.71 dB in terms of NMSC and 1.8 dB in terms of ACEPR. So yeah, here we have proposed a neural network which is actually inspired from memory polynomial equation. At the same time, like this has a provision to give priority based on the chronology of samples, which could prove important in these scenarios because the latest sample should have higher weightage always, and more combinations of those can improve the performance. Also, this has a much better performance compared to the conventional approach, roughly around 7 dB, as we have seen over the results, with generally lower complexity than most of the NN-based architectures that you see in literature. We also observed that by giving TANH as a activation function instead of leaky ReLU, especially for the fully connected part, we can further improve the results. So in future work, we can see like how this modeling can effectively build up simulators and things like that to design DPDs, which can actually send a linearly amplified signal, thereby improving the overall signal quality and hence the efficiency of the wireless communication systems. Yeah, these are the references. Yeah, that's it from my side. Open for questions.
Thank you very much for your presentation. Does anyone have any questions?
I can ask a question. This is Umut, and thanks for the very nice presentation. I'm curious here. So you have like some kind of fully connected neural network, right? And the complexity is comparably, I'll say, low. I'm not sure how many parameters you have here, but so like, did you try, like, for instance, fully connected neural network for a simple case, or like LSTM-like model for time sequences?
Actually, there are multiple models, neural network-based models for DPDs, which actually tries to model the inverse function of PA. So one of the recent publications were ETDNN, where they propose an architecture which has less compute by actually pruning the network after training. We were using that to start with, but then we had, because the score was open, how it needs to be calculated, that was turning at around close to 55. So because of the complexity still associated with it, even after pruning it.
Yeah. Okay. Yeah. I mean, it's not to just. I was curious, like, if this architecture provides somehow like a better performance or not. So this.
The performance was slightly better compared to ETDNN, but complexity was much lesser compared to ETDNN, and hence the overall score will be much better.
Also, I'm not much familiar, but like the time samples, you're doing some kind of feature extraction here, right? Like, if you were to use the same neural network for all the time samples, like, will it perform similarly, or like the effects over different times are like very different? So that
actually, there was one experimentation run using same parameters for all the past samples and different parameters for the current sample alone. But again, like when we look at the score wise, there was not much of an improvement or gain that we were observing because of that. I get your point, because the complexity will be very much minimized, because you need not have 10 such layers compute, because one such layer is sufficient, and you can just use the past compute of the second to third to 11th sample. But still the performance was dropping using that approach. So overall, score wise, it didn't had an improving impact. Rather, it was down by roughly a 0.5 to 1 dB in performance.
Yeah, thank you. I just wanted to, like, wanted to know about, like, if you guys tried like different solutions in general. Yeah, you seem to have gone out.
Yeah, we tried multiple other variations as well. I mean, we started with CNNs, we went to BiLSTMs, but the compute was playing a very huge role there, with not much of an improvement in the performance. So we wanted to have a much simpler network, at the same time having a performance that is comparable with any other neural network architectures that are there in the literature. And with this architecture, interestingly, we found that it slightly outperforms, apart from BiLSTM based architecture, in terms of performance in all the cases. And in terms of complexity, this is the least amongst all the neural network architectures that we tried, based on the architectures that are provided for DPD, learning DPD, that are there in the literature. Because that problem and this problem are very closely related. Here we are trying to model the PA function. For DPD, we will try to model the inverse of the PA function. So we took that cues and tried out models, but those were our observations and conclusions from that.
Makes sense. Thank you.
Do we have any more questions from the judges? Okay, well, I'd like to open the floor for questions from the audience members or computing teams.
Do you hear me? No correlation?
Yes, we can hear you.
Could you give me a possibility to share the screen?
We are still on this, not finished, so please wait a little bit.
Sorry.
Yeah.
I mean, we are still open for questions from audience.
Yeah, so I wanted to ask a little bit about the performance. So in terms of the proposed solution, right, and if you compare it with what is available in literature currently, how does it compare in terms of performance and what is available in literature?
Actually, if we are open to say sharing other results from here, like we had a pretty much similar architecture for DPD design, which is actually accepted in PIMRC. There I can show you a rough results of how it is taking with respect to other solutions, if I am allowed to.
A quick one is okay, yeah.
Yeah, sure. Just give me a moment. I was not expecting this, so sorry for the. Yeah. In comparison wise, like, but this is with different nonlinear degree and different memory, maybe more suited for that data. So comparison wise, like this is pretty much on par with, I mean, slightly less compared to BioLSTM, slightly better or pretty close, but much better than any other techniques in the literature, whereas the complexity was like higher than here we use generalized memory polynomial than memory polynomial, where cross terms also will come into picture. Is slightly higher than that, but much lower than any other NN based approaches.
Okay, thank you.
This paper is actually accepted in PIMRC. Is not yet available online, but hope it will be available soon. We have presented it, and then it should be published in a short while in IEEE.
Okay.
Yeah.
Okay, well, thank you very much for your presentation.
Yeah.
I'd like to next call
Okay. Thanks, and thanks all then. Bye.
Thank you.
I'm stopping the sharing of my screen.
Thank you. I'd like to next call no correlation.
Hello again.
Please share your screen. Please start whenever you're ready.
Thank you. So, welcome everyone. My name is Saifulin Karim, and I am the student of King Abdullah University of Science and Technology in Communication Theory Lab under Professor Muhammad Slim Aluni. And today we're gonna have a journey for a power amplifier fitting. The first question we will ask is, why do we need to do it? So consider conventional power amplifier presented on the left. So it's bulky, cost, and consumes a lot of energy. Sounds like not sustainable. So let's somehow improve the performance and reduce the complexity and the cost of this power amplifier. And I will not dive into details, but the most important part is to fit the model of the power amplifier. So that's what I have done during this challenge. We as electrical engineers like to draw schematics. And the power amplifier is presented like this, as you can see on the top. And also we as an electrical engineers like to see the spectrum. So on the bottom, you can see the orange spectrum is the spectrum, the input of the power amplifier. And the blue one is the spectrum output of the power amplifier. We can see that there occurs some frequency component that does not exist in the original signal. So we want to capture this behavior. Going to the right, we can see the simplest model of the power amplifier. We can see that it contains some linear part and non-linear part. So this non-linear part codes all these distortions and unnecessary frequency components in our signal. And but life is not easier. And the real power amplifier input-output characteristics is not like this. It has some memory effects. That is the main headache for researchers to overcome. During my journey, I considered different models, like started with memory polynomial models. Then I changed polynomial function to spline function, consider uniform and non-uniform, some model like Wiener, Gammerstein. I will not stop on that because they gave good performance, but not the best one. We are looking for the best one. So I found that all these four models is only like a particular case of more general one, so-called Volterra model. So we will start from the Volterra one and proceed next. So Volterra model is the most general model that can be applied for any complex valued system. And of course, power amplifier, because we have complex valued input, complex valued output. In order to understand Volterra model, consider it as a sum of infinite sum of kernels of different size. So we will not dive into deep detail. Consider 2D kernel. So output signal Y at sample N depends on input sample Xn and some function of the amplitude of the input signal multiplied by some adjustable weight. Then this is main term. All other terms are considering memory effects. That's why it is headache. So output depends as well on current input sample and amplitude of the previous sample multiplied by some adjustable weight. We can draw this sum as a like table. This part of the table corresponds to H00. This part corresponds to H01. This sample corresponds to this. We can see that there are many weights and they are all adjustable. As I mentioned, Volterra model is the most general model. So it will give us the best possible performance. But the drawback of this approach is the very high complexity. So I found, and then I found some papers related to this, that we can use orthogonal matching pursuit in order to, instead of using full kernel, we can extract the most significant, the most important one. The problem with that approach is that it is NP hard. So orthogonal matching pursuit helps us to find suboptimal solution in reasonable amount of time. Also, such approach makes our solution more robust, because in that case, I think you all understand that maybe some of these terms are linearly dependent, so we don't really need all of them. So orthogonal matching pursuit for Volterra gives us more robust, more, let's say, flat minima. If you know this term that was presented by Professor Jürgen. So, and this application of this approach gives us complexity reduction 8 times compared to Volterra model, with little changes in the performance. And we can see it now. As I told, let's take a look at the spectrum of input and output signal. So on the left, you can see the original Volterra model with first kernel, second, and third one. I considered only 3 kernels because of complexity. And reduced on the right. We can see that generalization is in general very good. So we lost some decibels far from the main lobe, but it's not so significant because we achieved 8 times complexity reduction. Here we can see the results for normalized mean squared error and adjusted power channel ratio. These 2 metrics were used to score the points of the teams. And we can see that original Volterra has worse performance in some cases than reduced one. That's what I mentioned, because this this table shows the normalized mean square error for first test dataset, second test dataset, third test dataset, etc. So we can see that for test dataset, reduced Volterra approach gives us much better results and more robust because normalized mean square error is higher. Yeah, of course, for those who confused, it is reversed. So it's -33, but it's like technical point. And we can see that adjusted channel power ratio for original Volterra and for reduced one is almost almost the same. Yeah, we have some losses in some cases, but this is due to these effects, small effects, which is considered in adjusted power channel ratio. But in general, still reduced model with 8 times less complexity is very good. So now go back to our approaches. Considered Volterra model, and I found an algorithm to extract the most important, let's say, features. Now, there is another way to attack this problem, is so-called non-convex method. So instead of choosing particular pieces of this matrix, on the right, we can force our model to have some specific structure that will catch all the most important features. Then I came up with non-convex model. It is non-convex because we have some convolutions that for ML guys, you can consider it as LSTM. We have some convolutions and we have some non-linearities. And of course, this is non-convex model and it is quite tricky. You have input complex valued, output complex valued, and the weights are complex valued. So it's not trivial to train it, but I found a way and I applied second order method to train this model. So complexity of each branch, you can see there are 5 branches. Each branch is 80 real valued multiplications. And then I use some model that I found from the internet, but we can come up with any model and we can use my, let's say, approach to train it. But unfortunately, the performance was worse than for reduced Volterra. Not so much, but still, you can see that spectrum is not so good. NMSE and ASEPR were also like a little bit worse than reduced Volterra. So I end up with Volterra approach with orthogonal matching pursuit. the complexity of this approach is 188 real valued multiplications. It is compared to previous team MLAB. As I found from their report, they had 1,100 multiplications. I have 188 real valued multiplication, that is 5 times less. My normalized mean squared error and a separate, performance is a little bit worse than there, but complexity is more than 5 times less. Yeah, so the table they showed in the right bottom side is not up to date. So maybe I can outperform them because my complexity is much lower. So thank you for the thank you. And if you have any questions, please feel free to ask.
Okay, so do any of the judges have any questions?
So maybe before maybe as judges are coming up with some questions to ask, I can go first as we are waiting for the judges. In terms of your analysis, right? If I'm correct, you use the conventional signal processing methods or more mathematical based or model based approach rather than data centric approach where you use machine learning models. If you compare why you choose this approach as compared to using the machine learning based approach, what was what's your thinking and what was the advantage of using this approach?
Oh, okay, thank you for the good question. So this approach, non-convex, is I would say that it is neural network because we have some non-linearity. This is non-convex, so it's like any neural network. So this is like a neural network with complex values, weights, input, outputs, and etc. This approach, Volterra model is, yes, it's convex model. As we found, using orthogonal matching pursuit, we can end up with much better complexity, much lower complexity, I would say. And why I chose them? Yeah, because I found that this was because Volterra approach, Gammerstein model, Wiener model, memory polynomial, memory spline, it's all, old school approach. And I wanted to find a way to improve them and compete with neural network approach. I'm the old school representative, if you wish. But yeah, and based on this challenge, we can say that old school is better in sense of complexity, 5 times at least, but performance is slightly, no, is better in case of neural networks. But yeah, that's the output of our challenge.
The next presentation will be on the problem statement classification of home network users to improve user experience. Our first team will be data ranges. Data ranges, are we prepared?
Yes, thank you, Mia. Let me share my screen. So first of all, let me start by thanking the organizers and the judges for giving us this opportunity to work on the problem and present our solution to such a big platform. So I would like to first introduce our team. We are all master's second year students in Oklahoma State University. And we have 4 members in our team. We have Bharat Raj Mupala, Kate Phelan, Srinivas Pramod, myself, and then we have Tarun Reddy in the team. So let's start by talking about the problem statement. The business problem we are trying to solve here is to improve the user experience of 5G network users by identifying the 5G network quality problems well ahead in time.
To get a better perspective of the problem, let's briefly talk about the network architecture of the 5G network. The image here shows a high-level view of the network. On left side is the terminal. It can be a mobile or router, which is used by a user to access the internet, and on the right side is the source server. And right in between them is the DPI device, the deep packet inspection device, which is responsible for conducting the network activities. This divides the whole network into downlink and uplink side. And this DPI device is also the main source for all the data which is used in our analysis. So there is also another important point which says that the downlink side problems are the most important things to consider in our identification of quality problems. So with this understanding, to be more specific on the problem we are trying to solve is to accurately distinguish between the users with bad user experience, hereby called as UBE, and good user experience users, hereby called as UBE, through the downlink network set indicators. Then moving on to the brief description of the data provided. On the left, we have the overview. Out of 15 plus indicators relevant to the downlink side, 8 were determined as the key indicators by the problem statement, and only these were provided in the data set. But the data provided was from real world DPI devices, while removing all the user information. And talking about the data set split, there are 150 training data points and 50 validation data points and 50 test data points provided for each of the class. And these data sets are actually provided in separate CSV files with one CSV file for each user and containing multiple rows of time series data. And briefly talking about the actual columns provided in the data, the first step of internet connection is establishing the internet connection using a process called three-way handshake, which involves 3 steps. So the first 3 indicators talk about the time interval involved in these 3 steps. And indicators 4, 5, and 6 talk about the data transmission process after this connection is established. That all of these 3 talk about the time delay in the transmission of data. Then indicators 7 and 8 are a bit different. They talk about the retransmission rates involved while the data transfer is happening. What is meant by retransmission is that during the data transfer, some of the data packets don't get transmitted, and these are needed to be retransmitted again. And these indicators talk about the percentage of such failed data packets which need to be retransmitted. So overall, the higher the values of these indicators, the slower the performance will be. And in addition to the data, there were some guidelines provided in the problem description regarding how to go ahead with the solution. So this starts with the statement. This starts with stating an assumption about the data. The assumption is that UBE users will be having higher indicator values and higher outlier proportions compared to the good users. And this observation can be used to define a threshold to identify outliers in the indicator time series and consider all the values above this threshold as outliers and use this outlier percentage determined by this threshold to classify the UBE user. To be more clear on this, let's have a look at the examples displayed at the bottom of the slide. On the left, we have the indicator 1 trend chart plotted for a bad user. And on the right, we have the same chart plotted for a good user. You can clearly see the bad user is having overall higher values in this indicator, and the good user is having overall lesser values. Additionally, there are so many peaks in the left chart for bad user, but compared to that on the right chart, the number of peaks are less. What all this means is that, let's say we choose a threshold of 100 based on the good user chart. and then we'll find very few outliers for good user. And when we use the same threshold determined from the good user and bad user, we'll find many values higher than that, and we'll find many outliers. So this is the basis of the idea provided in the problem description, where we define a threshold based on the good user and use it in bad users data to identify them. So initially we tried to utilize this approach as it was provided in the guidelines, and we did data exploration in the same line, but we found some observations from that. So the first step we did was to visually inspect the individual indicators for each user using by plotting them. When we observed the outliers, we did see the assumption stated in the problem statement was true for some cases. For example, in case 1, you can clearly see the red UV user is having higher values compared to the UG users. But this pattern was not consistent when we observed other pairs of users. For example, in case 2, we can see the good user is having much higher values compared to UB user, like when we're plotting them on the same scale. So this made us revisit our assumption, and also it pushed us to consider other methods other than the guidelines provided. But anyway, we did continue exploration in the same direction. I briefly want to talk about this exploration before moving on to the final model we used. So we plotted all the 8 indicators for a pair of users from bad and good class on the same scale. Then for this one case, we can see almost all the indicators are having high values for bad user, but compared to the good user. But when we look at another case, similarly like before, again we have UG users with high outliers. So this again gave us pushed us towards utilizing other methods. So, but anyway, we tried to use statistical methods apart from visual representation to find a threshold. And this approach is not the final approach, but this approach involves using the 95% value as the threshold. So by definition, whenever we use the 95% value as a threshold, there will be 5% outliers. So our idea is to determine all the 95% values of the good users and use one of those values as a threshold in UBE and expect UBE to have higher outlier percentage. But when we again plotted the 95% values for all the users, the x-axis of these plots are the user numbers and the y-axis are the 95% values. We can see there is some clear difference in indicator 1, 3, and 4. If you look at the scales of it, the bottom charts have lower scales, lower maximum values for good users for indicator 1, 3, and 4. But for the rest of them, again, there is a mixed pattern. And since we did not see a clear differentiation between these 95% as well, we did not want to use this threshold approach. But anyway, we did try using this, but there were many misclassifications and the accuracy was much less than 50%, which is much worse than predicting at random. And then we again tried to combine the indicators just to see if this would help. So we used two approaches to combine the indicators. One is by functional understanding, another one is by principal component analysis. By functional understanding, we did two things. Since we are having multiple rows with the same timestamp, we assumed them to be relevant to the parallel events happening when user performs an activity while browsing. Like if someone clicks on the next page, there will be multiple service calls in the background. So we grouped those events together. And we also aggregated the 1 to 6 indicators because they occur in a sequence based on our understanding. But for 7 and 8, we averaged them instead of because they are percentages. And after doing that, when we did the same analysis in the previous slide, we did not again find any clear differentiation. Neither the statistical approach gave good classification either. Then the other way of combining these indicators was principal components. Usually 2 principal components would capture maximum variance, but here again we needed 5 plus principal components, and they did not help in reducing the dimensionality. So that's when we wanted to move completely towards machine learning methods, which I'll be walking through in the next slides. And before going to the machine learning methods, we also had another reason for considering machine learning methods. Until now, the focus was on the absolute indicator values, but the experience is dependent on many other factors like network fluctuation and with several scenarios. We can take a look at 3 different scenarios where more than absolute values are relevant. For example, a user might have high-speed connection and the short, which will result in short connection times and lesser outliers. But at the same time, there might be a lot of network fluctuation and the user might report a bad experience. So short, lesser outliers may not always mean the user will report good experience. Similarly, in scenario 2, there might be very high volume downloads resulting in large connection times and large outliers, but the user might report a good experience because the times were expected. And similarly, in the third scenario, there might be a high-speed connection, but there might be a lot of connection failures, but the user might not report a bad experience because he uses it very minimally and the speed compensates for the issue. So there are several scenarios which prompts us towards exploring beyond absolute values and outliers. So with that understanding, we tried utilizing several modeling approaches for longitudinal and time series data. There are 5 methods we tried. The first 2 methods are again centered around anomaly and outlier detection. But here we don't use an absolute threshold, but we try to use identify the anomalies based on local variation. And there are 3 more approaches. The third method is called date time. It is called time warping of time series, which is based on determining the similarity between 2 time series and classifying the time series to the class which it is more similar to. So the first 3 approaches were very time taking because we had to use all the 150 training data points to do that for each and every new user we test on, instead of just testing on having one model and using that to predict the new user's class. We have to use all the 150 user models, and the accuracy was not good. That's when we moved to the method of feature extraction using wavelet transformation. So to briefly explain about wavelet transformation, basically it's a signal processing technique where we divide the whole time series into smaller time ranges, and for each time range we assume a wavelet, which is a small wave, which can represent the time series. So we will assume a shape of wavelet and we determine the frequency, which is able to represent the time series in that time range accurately. So there are 2 types of wavelet transformations. One is continuous wavelet transformation, which is called CWT, and we have discrete wave transformation, which is called DWT. CWT gives a large range of waveforms, while discrete wavelet transformation gives only few waveforms at different frequencies. So when we tried all these methods, method 5 is the one which gave us the highest accuracy of 64%. All rest of them gave only about 50% test accuracy, which is as good as predicting at random. So we have finalized our model as DWT and combining with the different ML classifiers. So focusing on this method, we have generated 3 different set of features. The first set was solely based on the group data, which we described in the previous slides, where we group the data by timestamp. And then there are 2 more data sets is generated where we first do a principal component analysis on the first one to reduce the multicollinearity. And then we proceed with the wavelet transformation. And we had the same pre-processing for all training, testing, and validation data sets. And then within each of these data sets, we further had 6 different wavelet transformations. Because since we did not know which wavelet will be capable of accurately representing the time series, we experimented with 6 different wavelet transformations. So we have that on the screen. DB2 and DB5 belong to the same family of wavelets, and the rest of them are different family of wavelets. So in total, we had 18 different feature sets to experiment on. And after this features were extracted, we trained, we used this for training 10 different classifiers. Again, this was needed just to make sure, like, to find the most effective classifier useful for this current data at hand. And in the first experimental phase, we identified random forest and nearest neighbors has the highest accuracy of 62% and 63% respectively. Then once this was identified, and the wavelet used for these models are different, which you can see in the selected models box on the left. And once these were identified, we proceeded with the hyperparameter tuning, which involved 2 stages. One where we test a wider range of hyperparameters using random search CV. And once we found a closer range, then we use the smaller range again in grid search CV to find the most optimal hyperparameter. And the final model we selected was the random forest model, which uses DB5 wavelet transformation. And it was without PCA because we are getting similar results with PCA as well. And once this model was finalized, we save this as a pickle file and then use that to predict the test data set of 50 users in each class. And we can see the confusion matrix, AOC curve, and other metrics on the screen. And one thing which we should observe is the precision, recall, and FN score for both the classes are pretty good, and they are above 60, which is a good sign because the classifier isn't biased towards any particular class, and we can see the overall AUC curve is also quite good, and the accuracy was 64%, and we finalized this as our final model and uploaded it as a solution, and which gave us the highest ranking in the problem statement group. And what we can conclude from this that the best accuracy is achieved using time series transformation and machine learning methods instead of solely relying on outliers. And such identification has a great business value in long term, as users' problems can be solved proactively before any complaints are raised. And 64% is a good accuracy, I believe. Talking about future scope, even though 64% accuracy is decent, if we have more informative variables, we can achieve higher accuracy. As observed previously, we had 15, but 15 indicators, but we used only 8 of them. So if we have more variables, we can get higher accuracy. And in this case, since we are using feature extraction, we can definitely get more higher accuracy. And also we can experiment more with more mother wavelets, and there are some other optimizations we can use for the wavelet transformation, which might improve the accuracy. So with this, I conclude my presentation, and we are open for questions. Thank you.
Okay, thank you very much for your presentation. Could I first ask the judges if they have any questions? Okay, just a quick question for myself. Did you try any other approaches such as deep learning or?
We did not try neural networks because we believed that might not perform good performance in terms of the time it takes to run, because that's one of the criteria for judgment. So
Okay.
yeah, that would have been another approach. Yeah.
Sorry?
That would have been another approach to try. Yeah.
Okay. Okay. Well, thank you very much for your presentation.
Yeah, thank you. Thank you for the opportunity. Thank you.
Thank you. I'd like to next call on, don't know how to pronounce the team name, Shiding.
Yeah, one sec. I'm gonna try. Sorry, you guys able to see
Please
my
start whenever
screen?
you're ready. Yes, I can.
Okay. So hi everyone. I'm Rashad. I'm a third-year undergraduate student at the Chinese University of Hong Kong, and my team name is pronounced XDDing for reference. It's just a team of myself, and this is my presentation on machine learning models for home user network classification. So just an overview of what the presentation is going to be about. I'm going to start off by talking about the problem statement, like what the problem statement is about, what's the motivation around it. Then the data, which is the analysis of the data that is provided for this problem statement and the challenges that it presented. And then finally, the viable solutions that I was able to come up with to deal with the challenges that the data presented. So this is the problem. I'll go over it quickly since this is already discussed by the previous team. Essentially, the motivation is that user internet experience is becoming a top priority for network operators worldwide, with the growing number of users. And predictive models can help these operators discover potential complaining users in advance. So ZTE, the challenge organizer, has in the description mentioned that the kind of experience that the user is having is heavily dependent on 8 key indicators from DPI probe readings, that is the downlink network side. So that those are used as predictors or the features for this problem. So this is a bit just more details about the 8 indicators. Since the previous team discussed this, I'll just point out some key things. The first 3 indicators all have to do with the three-way handshake or the TCP handshake between the SYN-ACK packet and the ACK packet, then the SYN-ACK packet in the second step, and then the time interval between the ACK packet and the first payload packet. And the last 5 have to do with TCP transmission. And another thing to note is that the first 6 indicators are all time periods, and the last 2 are percentage based. So these are the labels that we aim to classify for this problem. So these are just 2 samples. You can see on the left is a user with a bad experience, hereby referred to as a UBE. And on the right is a user with a good experience, hereby referred to as a UGE. And as you can tell by the images that there are some features that in general, the assumption is that users by experience will have more outliers. But if you can see perhaps like indicator 6, you might be able to tell that even a UGE has a lot of outliers or at least spiky data points in their data as well. This is something I'll cover more in the data section, but just keep that in mind. So this is the data section, just an overview of what the data looks like. We're given records of 500 users. There's generally 8 time series of indicator readings per each user. And the time span of these ratings is usually like a week. The class distribution is 50-50 between UBE and UGE, 250 each, which means accuracy with a 50% threshold is a good metric for this problem statement. And that is what I've used to evaluate all the models that I'll be covering later. So this is the first 3 challenges with the data. The first is, of course, as you might have noticed already, there's a small sample size of 500 users. The second is that some of the observations are very dense, going up to almost 44,000 observations, and some of the observations are very sparse, like only about 566 observations per user. And this is because the sampling rate and time range of the records are actually not standard. You can see on the image on the bottom, on the bottom left, is a user with a different time range than the image on the bottom right, which is the another user. And then if you look at the circle at the bottom, you'll also be able to see that the sampling period between the two records is also different. Another challenge with this competition is that there, in almost all of the data that we're given, in almost all the records, there are multiple observations present for single timestamps, and we don't really know where this originates from. It could either be a mislabeled time itself, or it could be multiple readings that are taken within that time range and then rounded up to the closest 5 minutes. So this is another challenge. We don't really know why there are multiple observations for a single timestamp. And this is back to the difference between UGE and UBE. So as I talked about briefly, as I touched on briefly in the indicators with UGE and UBE slide, even UGE data has outliers. And on top of that, I strongly suspect that the UGE and UBE label is user reported. And this leads to different standards by user on what is a good experience or a bad experience. For example, someone with a good experience, someone with a heavy requirement for internet access, a heavy internet user, might think that something is a bad experience when somebody with a lower requirement or using the internet less frequently would think the internet for them is just fine. And these two things combined leads to very similar statistical distributions for the indicators in UB and UG. So the box plots on the that you can see here are basically the red ones are UBE and the green ones are the UGE counterparts. And as you can tell, the distributions are barely distinguishable. And this actually leads to a lot of problems when trying to run traditional statistical methods with the raw data, which I'll get to in the next part. So to start off, my solution, to start off the solution part of this presentation, first I categorize this into a multivariate time series classification problem. This problem, it is essentially defined as a machine learning problem where you use multiple parallel time series to classify, to predict them into a label, which is exactly what this problem is about. And after conducting experiments with many different methods, there are two promising model architectures I'd like to present. The first one is a deep learning based RNN approach, and the second one is a more traditional feature extraction and then XGBoost classifier based approach. So to start off with the deep learning approach, we need a pre-processing pipeline is needed for this because of all the data challenges that I mentioned earlier. The first part in my data pre-processing pipeline is a method called regularization method called linear interpolation. And essentially what this method does is that it resamples the time series to a fixed interval. For this problem, I chose an interval of 5 minutes, but in the example on the slide, the interval is 15 minutes. From the picture itself, you can tell that the gray points is the unprocessed time series, and then the orange points are the new ones after processing them using linear interpolation. And this method allows us to deal with a lot of problems at once. For example, the uneven sampling rate gets fixed because it's sampled to a standard time range of 5 minutes. Then the dense time series, a lot of them have like multiple observations for the same data point. They also get evened out and regularized by this technique. So, and that basically we can get almost 95% length reduction in time series while still preserving their predictive power. The next step of linear interpolation is Z normalization, a method I'm sure everyone is familiar with. For time series analysis, it allows the models to focus on structural similarities rather than amplitude-driven ones. And this helps our models a lot since, as I mentioned earlier, some of the features are in percentage values, some of them are time samples, so the scales differ and the units are not the same. And Z normalization really helps to deal with that. And then final step in this pre-processing pipeline is low noise padding. Low noise padding is a pretty simple thing to understand. It just suffixes low amplitude noise to any time series, any shorter time series, to make it as long as the longest one. So if there's a 10,000 length time series, the longest one, and there's another one that is 900 points long, there will be up to 900 to 10,000 will all be a low amplitude noise. I consider other methods for padding as well, such as uniform scaling, truncation, IRMA-based future value forecasting. But in general, studies have shown, and even in my experiments have shown, that these methods tend to not perform as well as just a simple low amplitude noise padding. And this finally helps to deal with the uneven length time series problem, where the data ranges are, where the density is different. So this is the model itself, the deep learning model. LSTM-RNN is a well-established model for deep learning-based time series classification, or any deep learning-based time series task. I'm sure everyone's heard this at this point. My model turned out to have 1.3 million parameters in the final version. It took around an hour to train on a single P5000. I used 80% of the data as a training set and 20% of the testing set, because generally deep learning networks have higher data requirements. So to help it be able to generalize better, I just used the validation set as a part of the training set as well. So this is a solution for LSTM-RNN. I believe that this is the most promising solution given more data availability. The tested accuracy was 58%, which is actually an 18% accuracy, up to an 18% accuracy improvement over the traditional methods that I tested, which is like traditional multivariate time series classification algorithms like Rocket or dynamic time warping, k-nearest neighbors, and many other classifiers. So an interesting pattern can be observed in the training loss graph, training and validation loss graph, is that after around 5,000 steps, which is where the best model epoch is, the training loss becomes erratic and the validation loss begins to spike. And this is, of course, a classic case of overfitting. But the fact that the training loss is not dropping, but instead erratic, leads me to believe that it's actually the model is actually just unable to find more predictive features. And with this in mind, perhaps with more user level data, like more than the 500 that we provided, this model might be able to reach a much higher accuracy than the next solution that I present, which is the best accuracy that I achieved with the current data set. So this is the solution that I'm talking about. It involves 3 stages. The first one is using a tool called TS-Fresh. This library just automatically extracts thousands of features from the time series to give new insights into the dynamics. So from the picture itself, you can tell it extracts basic features like maximum, minimum, medium, mean, number of peaks. And then it goes even further to in other domains like frequency domains, so it calculates Fourier coefficients, or even autocorrelation coefficients. Just thousands of features that you might not be able to think of manually. The benefits of this technique is that there's no pre-processing pipeline required, since you're directly calculating the features and statistics from the time series. And after applying this tool to the dataset given, I was able to extract 6,242 features for each user. So of course, that is a lot of features, and to solve this, we need a dimensionality reduction technique. So this is a classic case of the big PLN problem, which is essentially just when the number of features or the number of columns are much more than the number of rows and in any data set, and that violates the base assumptions of many machine learning algorithms. So for dimensionality reduction, they use PCA, principal component analysis, with min-max normalization, because it is a required pre-processing step for PCA to normalize the data. And this finally brought the final features down to 397, which is much more reasonable to work with. And this data is finally plugged into an XGBoost classifier, which is well known to be a state-of-the-art gradient boosted classifier. It's robust, it's fast, it's repairable, used in all kinds of problems to offer the best solutions in like many problem domains. So this is the final results for this approach, which I've called the TS-Fresh approach. And it's the best performing model with the provided data. The tested accuracy was up to 67%. It hovers between 65 to 67%, depending on the random component of PCA. This is a 12% improvement over some models I tested with manual extracted features, which is basically I defined a set of features to calculate from each time series. For example, the percentage of outliers using local outlier factor, or mean absolute deviation, and descriptive statistics like mean, quartiles, median. It offered 12% improvement over that, which tells us a bit about the data, and that the immediately obvious statistical distributions don't tend to offer much predictive power. This method has a total runtime of around 2 hours on an 8-core CPU machine. It does not require any GPU at all. And for this, I was able to use the original data set training set provided by ZTE, which is 300 users. And the testing set is the same as the previous one, which is like the same 100 users. And for metrics, you can see on the right side, performance is quite satisfactory. And yeah, that's it for my presentation. And I'll be taking any questions now.
Thank you very much for your presentation. Could I first ask if any judges have questions? Goranga, please ask your question.
Hi, Rishad. Thank you for the very nice presentation and very nice work. So regarding this TS Fresh, right? And you initially said that you were suspecting that there might be some variance across the users too, right? And the TS Fresh that you have done is the features that you have extracted is user-based features. Now, and from there you've done PCA to downsample it to some 397 or some numbers, right? Did you check like across the users, are there any overlap in the, let's say, top 50, top 100 features, or is it random? Did you do some analysis on that?
Yeah, so I did consider that, but actually the thing is like PCA makes this kind of analysis very hard because you cannot really tell where you cannot map it back to the original features, right? So yeah, it is difficult. Like I even tried to offer like feature importances and stuff.
Yeah, like even I'm thinking more from the final outputs, like when you're training the neural network model, you go back and you try to see like the importance of each feature, and from there maybe you can figure out.
Yeah, exactly. So that's what I'm talking about. So I would have loved to do that, but the PCA makes it very hard to map it back to a feature importance. That's like, it's very hard. I would have loved to do that though.
I think yeah, if you can, even with the PCA, if you just try with, I don't know, 6,000 features and try to see if there is something that because if your guess is correct that there is a variance across user, and this is user input of whether the network is good or not at that point, then this is something that you can actually prove that, okay, like even for this, your RGE and I forgot the anyways, so you can actually learn a lot from that. Anyways, yeah, thank you for the great work.
Yeah, thank you for the session.
Do any other have any questions?
Just a quick question from me, maybe. So in this case, you have done you have used XGBoost to rank important features, right? So in the case of using, did you use like only XGBoost to find the performance of the model at the end, or you just rank the important features and then move to LSTM?
No, so essentially there are two different solutions, right? So the deep learning network is different and the XGBoost solution is different. So they're not used in the same pipeline. I just offer two different solutions because I believe the deep learning approach will be able to give a much better performance if more data is available. But with the current set of data, the XGBoost method is performing the best.
Okay, thank you.
Okay.
Can I ask a quick question? Thanks, Rishad. Excellent presentation. Slide 9 is really interesting. You have actually analyzed the data pretty well. I see that you're saying user reported. Why do you say that? Because all the indicators looks like coming from DPI. So why do you say it is user reported?
Oh, no. So I'm not, so by user reported, I meant that, so like, how would you classify if someone is having a good experience or a bad experience? So I just have a suspicion that they maybe some kind of survey or some feedback was taken from the users, not the DPI readings, but like, to ask them if they were having a good experience or a bad experience. That's what I thought. But if it was labeled by a professional, then my assumption is wrong.
Okay, yeah, okay. Then your comment is on labeling. Okay. Yeah, I get it now. Right. So you're saying there are similar statistical distributions. That is, especially in indicator 7. I don't fully understand how that can come about, but it is quite interesting slide anyways. Do you have some insight or comment why this is similar? Is it because of measurement problems, or is it because of labeling problems? Because the indicators, if I look at indicator 7, if your second plot, indicator 7, that's actually, there is, I mean, I don't see how they can look similar.
Yeah, that's a good point. So those graphs were basically just taking aggregate of all the readings together. So it's like just describing the overall distribution. But maybe for like specific use cases, if you apply a bit of pre-processing, it'll be easier to tell the differences. But yeah, that's just what my analysis showed. I'll look into indicator 7 more.
Cool. Yeah, and thanks for TS Fresh. That's quite cool too. Yeah, thanks.
Yeah, no problem.
Okay, do we have any other questions? Okay, well, thank you very much for your presentation, Roshat.
Thank you.
I'd like to move on to the next team. Spears 9. Are you ready? Oh, I believe that we can't hear you.
Okay.
Oh, we can hear you now.
Yes. Hi, everybody. Let's talk about our 5G challenge on classification of home network users to improve customer experience. Firstly, I would like to thank everyone for this opportunity. We had a really good experience in working on this project and working on such kind of data set. It has given us, even me and my team members, a really good exposure. I would also like to mention that it was a team effort during the whole project, but to save time and easy transition, only 2 members are presenting today, me and Hayden. Going on to the next slide. This is my team of 5 members. We are the Spears 9, representing Oklahoma State University. We have Hayden, Kumar Yash, Anuj, Sushma, and Moon Chavi. We'll go to the next slide. This is an outline of what we will talk about in the presentation today. We have the data background, the problem statement, data cleaning and outlier detection, model evaluation summary, indicator importance, business recommendation, future scope, conclusion. We'll go to the next slide. Let's talk a little bit about the business background. The home broadband system has become an important component of many people's daily lives all over the world. This growth has created a market that is becoming increasingly saturated. It all depends on the user experience and the quality of broadband networks. The user experience is influenced by many factors. The uplink network side and the downlink network side are the 2 sections that separates from the broadband end-to-end network. The diagram here depicts the network layout. A significant part of the network issues are downlink network side issues. We would start analyzing the data and discover that a user may encounter a variety of issues and have either a positive or a negative experience within a certain time frame. In the future, operators will be very concerned with accurately representing whether a user is actually bad or good, so they can predict that before it occurs. Moving on to the next slide. Let's talk a little bit about the data. The data contains 8 indicators, which are mentioned below in the slide, which depicts the time delays at different stages of packet exchange in the network for the users. The indicators are obtained from the 3-way handshake process and the data transition process after the handshake is successful. The indicator 1, in the first step of the 3-way handshake, the time interval between the snack pack and the atom packet. The indicator 2, in the second step of the 3-way handshake, the time interval between the snack packet and the atom packet. The indicator 3, the time interval between the atom packet and the first payload packet in the 3-way handshake. Indicator 4, the response delay of the first packet with the payload after the establishment of TCP for multiple flows in the session. Indicator 5, in TCP transition, the actual delay of transmission from the DPI position to the user terminal. Indicator 6, in TCP transition, the transmission delay for the DPI position to the website. Indicator 7, in the TCP transition, the percentage of the downlink transmitted packet in the current session. And indicator 8, in TCP transition, the percentage of upstream retransition packet of current session. Additionally, the data included day, hour, time, and 8 indicator variables for each good or bad user experience. Apart from that, there are 150 users. 50 users each have good or bad experience as a train, validation, and test data. And we go over to Hayden.
Thank you, Chavi. So initially what we did to detect our outliers here was we used a IQR method to detect them. However, instead of using the 25th and 75th percentile, we used a 4th and 96th percentile. The reasoning behind that is if we use the traditional method, then 20% of the overall data would have come back as a quote unquote outlier. So by doing that, we saved 20% of the data and we're able to use that in our modeling. Moving on to the next slide. We aggregated each user's data into one single record, and we did that by different fashions. So we merged the data on an hourly, a multi-hour, a per day, and a full time period, and then tried modeling. While merging, we tried different ways to aggregate that data, and that was by taking the mean, the median, the minimum, and the maximum. We found that the total time period was the best fashion of aggregating the time, and we used the min-max scaling. By doing that, we got resultant values ranging from 0 to 1, and that reduced the standard deviation to minimize the effect of our outliers. Moving on to our next slide, in the model evaluation, on the graph on the left, you can see that 57.6% of the model was accurate. And after using the turning in our report and using different data that we built our models upon, we got a 61% accuracy. So it did improve a little bit. And then also the logistic regression is the best performing model that you can see, but it's also the simplest and easiest model to interpret and create. The graph on the right indicates how the model learned over time for the training and validation data. And as you can see, the validation set started to perform a little bit better as time went on. Next, we'll talk about the indicator importance. So the graph on the left shows all of the indicators and their importance. Indicator 5 was the actual delay of transmission from the DPI position to the user terminal. And that is the bar with, that is the tallest on the left-hand side. And then indicator 6 was the transmission delay from the DPI position to the website. Those two were by far the most influential indicators that we were given. And then if you look at the bottom right of the graph, indicator 3 is very low and seems to have little to no influence over any of the data. Next, we'll talk about our business recommendations. So we would like to anticipate customer needs and prepare for them, prepare operations to meet them. We also want to handle issues before customers face them, which was the goal of this project. We could launch surveys or marketing campaigns to figure out how much money a bad user experience is actually affecting the business, and provide them assurance that they can get help wherever they need it, whenever they need it. We also want to harness customer data to reduce churn and give faster resolution to customer issues. So if we're able to predict these issues before they're happening, then try to find a resolution as quickly as possible. Lastly, for the future scope, the reasons for the transmission delay are clearly the most important and could be investigated a bit more. However, if we were given location data, we could dig deeper into if one user is having a bad experience and take action. That could be, is the population very dense? And that's why they're having a hard connection. Or you could look at the pricing option of the customer. Maybe they're not paying enough to have the broadband speed that they're expecting, or they just have high standards and have the fastest network possible, but it's just not performing to how they would like it to be. We could use a little bit more detailed information about the indicators, or even more indicators in the future with this project, as that would most likely increase the accuracy of these models. Thank you guys for your time and for the opportunity to speak today. We really appreciate it, and we had a great time doing this. And we're now open for questions.
Okay, thank you very much for your presentation.
Absolutely.
So I ask the judges if anyone has any questions. Everyone, thank you.
Hello, thanks for this nice presentation. From your appendix part in your presentation, I can see that the correlation of indicators are not so much correlated. We can say that, I mean, from the appendix, I can see that the mostly correlated indicators have nearly 0.4, right? So have you ever tried just univariate prediction in your all models? Maybe, I don't know, maybe univariate itself may produce close performance as you did with other models. Have you tried such kind of things?
Initially, we did try to treat it as time series and do the univariate for prediction. But upon further investigation and upon further data transformation that we thought best, we took out the time feature out of the data. We kind of merged the data for, so we had individual users for whom we have the data for each timestamps, around 10,000 those for each user on an average. So basically, when we talk about user experience, we don't say we have a bad experience at that particular minute or that particular second. We kind of talk for our experience, we kind of say, okay, we are having bad experience with this particular network provider. So we did what we actually do in real world scenario. We took one particular user and created a single record for each user, saying that this user had bad experience overall, because that was the data that we got. We had the complete data file for each user, but technically we only know that that particular user was having bad experience or good experience. So we kind of merged the whole data into one single record, and it took out that time feature out of it.
Okay, thank you.
Okay. Do any of the other judges have any questions? Okay, I'd like to open up the floor to audience members and other competing team members if you have any questions.
Hi, can I ask a question?
Yes.
Yeah, sorry, I don't really know how to raise my hand. Sorry about that. Yeah, so actually, I just wanted to, I don't know if it's a question or a small correction, but like I noticed on one of your slides, you mentioned that there are 150 users, and that and the data points are essentially, each user has like a UGE time series and UBE time series, right? But in my experience, I found that even though the labels are the same, for example, like in the training set, there could be a user one in UGE and then user one in UBE. They actually had different values for the same timestamps. So do you have like any information which leads you to believe that they're actually the same user?
So maybe like the wordings were a little wrong, but the what we meant was we had like 150 users as a good experience in our test data, and 150 users in test data which had bad experience. So we kind of took all the 300 users together and assigned one flag variable to each of them, saying that this user was good and this was bad. We were not treating them as like user one in good was not same as user one in the bad. So maybe the I can acknowledge that the wordings were wrong, but this is what we wanted to say or like portray.
Okay, yeah, that's totally understandable. Thanks. Great presentation, by the way.
Thank you.
Okay, does anyone else have any other questions?
Yeah, maybe a quick comment. Nice work. I think you have applied the machine learning techniques nicely. I think from a domain expertise perspective, I just want to make a quick comment. The location doesn't matter. I think in this particular problem statement, as far as I know, location doesn't matter. The another thing which might, which kind of, I mean, it's quite interesting that you have done it, but it doesn't go well. That with at least my understanding is that time taking out as far as TCP traffic is concerned is it doesn't fit well. But your results are interesting. So I mean, there's quite an interesting path to take.
Initially,
but if
like
you
when
if you talk to
sorry.
Yeah, go ahead.
So based on what you just said, so initially we were looking at as time series, and first issue that we figured, like, so what knowledge we had as a team, so we knew what time series was, what like a two-dimensional time series, like multiple users having their data recorded at time series. But it was
we lost an looks like.
I think we
there were
might have
multiple
lost.
records. It says 6 hours, 59 minutes, 59 seconds. So there were multiple records. So very first thing was data understanding for us. And upon, like, while we were searching, so we came across, we did not have any domain knowledge. So we came across Fourier transformation for time series to frequency, changing time series to frequency domain and all. So we were trying to apply that knowledge, but we were not getting the results that we wanted. So after that, we had to change our approach. So we wanted to do what we could do at that point of time. But yeah, I do agree that after seeing others' result, after seeing like LSTM and CNN and TS Fest, as Rushat mentioned, so initially we were also skeptical that getting 57, 62% accuracy might not be enough. But even the deep learning, we did try deep learning approach. And for that, we were getting around 70% accuracy for validation. But on test data, it was like only 48%. Even after hyperparameter tuning, like there was no much improvement. There wasn't much improvement. So we thought that logistic regression is giving best results so far. And even after the submission on the test data that was used by organizer, that was not provided to us. That particular model was giving even better results compared to what we were getting from logistic regression.
No, it's cool. It's a different perspective. Yeah, thanks. Yeah.
Thank you so much.
Okay, thank you very much for your presentation. I'd like to now welcome our final team for the problem statement, Build Your Own Closed Loop, InnovNet.
Yes, I'm here.
Okay, if you could share your screen. Thank you.
Let me know if my screen is visible.
Yes, we can see your screen.
Okay, let's start. Okay, here's Tariq Muhammad, and I'm presenting a demo for driving new use cases based on the link prediction algorithm. Actually, this work done by only me and was mentored by Dr. Vishnu Ramov from the ITU. This is the content of our presentation. We will walk through our problem and also the existing solution and what we propose to solve this problem, and also the reasons why we can use this pipeline or this mechanism. Last thing we will talk about results and recommendations from our side. Okay, what is the problem? Okay, autonomous network has gained a lot of reputation in the past few years. Actually, this event happens because of the autonomous network. We all presenting solutions and presentations to present new use cases for autonomous networks and to get the help of artificial intelligence in our telecommunications network or any other kind of network. Last year, this problem is yearly based. That means that every year we have a lot of different use cases, which means that every year we have new use cases. This new use cases mainly comes from the old use cases. We try to enhance the old use cases by discussing or discovering new use cases. By this task or for this task, we can use the help of machine learning and artificial intelligence also to get this task or to get a new use cases further without the need of the human actor or by reducing the need of the human actor. Actually, this is the closed loop that we propose. We have an ML in top of our source code or our source representation or reference code and so on. By using this, we can predict or we can have new use cases. Okay, let's ask a question. How do we discover the new use cases currently? Currently, we depend on the human actor and the experts to discover and test the new use cases according to the old ones. So we are discovering the old use cases, then we tested or we try to discover manually what is the new use cases. This process is time and effort consuming, and these factors are very important for any kind of business because this resources means money, and we know that in the era of 5G and 6G, we are searching for a new new revenue channels. Okay, so this is our main focus here is to provide a new use cases for the business. Okay. Let's try by explaining our whole pipeline, and next we will deep dive into first block of our pipeline. First, we start with the use cases document. ITU has a document that contains all the current use cases or all the old use cases. For this document, we have requirements for each use case. We have graphs as images that represents some of the use cases, not all the use cases. And also we have a metadata that represents the use cases itself. So all this document that represents the current use case. So the first step is to parse this document very well to be able to capture all the requirements, all the metadata, all the information about the current use cases, to be able to predict new links or new relationships or new use cases in the future. So we use this parsing part to generate the reference code. Also, we use this parsing to generate the reference code, and also this parsing is used also to make the graph representation directly. We can see here we have two lines. One to generate the reference code, then go to the graph representation. Next one is to use directly the parsed figures to go to the graph representation. The reason of that because here in this document, the graphs or the images do not represent all the use cases. So by the help of Dr. Vishnu and his work,
on the reference code, we are able to capture all the use cases in the document, which was around 40 use cases. But only if we use the graphs as images, we will use only around 10 use cases, which is not representable for all use cases. So for this reason, we have these two lines here. And actually, in the graph representation, we have three scenarios, which we will talk about later. Okay, and after making a graph representation or a graph database representation on the parsed on the data we have, we will apply the link prediction. This link prediction is trying to predict new links between the network actors, between any two different actors in our network. So we need to predict what will be the link there, or if there is a new link that is not there. And the result of this link prediction algorithm is supposed to produce a new use case document, or supposed to produce a new use cases according to the new links that is discovered by the algorithm. Okay, this is the overall. Let's deep dive into each part of what we have talked about. Let's start by parsing the document. We have mentioned that the document has three main parts. We have parsed the requirement, and we have parsed the metadata. And actually, we faced some of problems, but last we come up with a table, with one table that represents the whole metadata and requirements in this stage. So we have one row for each use case. So this row contains all the metadata and requirements together for each use case separately. And also we parsed the figure, but we have a problem that figures in the document was not represented as a parsable format. We know that images is not a parsable format. So first we need to convert the images into a parsable format. Then we use this parsed format to represent the relationships found in this figures. For this task, we used the plant.uml tool and also the draw.io tool. We found that draw.io is the best one to represent images or to represent the sequence diagrams, and we ended up with a table like this. This table represents all relationships found in all use cases. So in each row we have one only relationship. We have the source and target, the message itself, and also the class of this relation, and also this ID. This can be used further to make the graph representation. Let's talk about next step is to make the graph representation. As I mentioned, we have three different scenarios. First one, we can use only the document figures, which comes from the document images itself. But this scenario is has a very important disadvantage, which is it's not representable for all use cases. Okay, but it represents well only the use cases that have images on it, but not all use cases have this part. This is the first scenario. The second scenario is we use the reference code. Dr. Vishnu made a lot of effort in this part to make the reference code representable for all use cases to make us able to make the next step. The third scenario, we have used the reference code only, but also we have added the functions of the network actors or the network elements as a node properties for each network. In the graph representation, we know that each node has some properties. So we added the functions of the elements as node properties, or as properties in these nodes. So this is the third scenario, which we contributed a lot in this one. So next step, we want to add some additional properties or some additional features that can help the link prediction algorithm to predict the new links between any potential two pair of nodes. So we have added some additional properties. We have mainly we have added three properties. One is the community detection property. Second one is the centrality property. Third one is the node embedding one. Okay, we have added for each node, we have added these three properties to be able to predict the new links. Next step is we calculated the combined feature. By combined feature, we can imagine it as a similarity between any couple of nodes, any pair of nodes. We are calculating the combined feature for all properties we have. So for all properties and for each pair of nodes, we are calculating a combined feature. The next step is to apply our length prediction algorithm, which we can imagine it as a classification problem, in which we classify the true relationships and the false relationships between any pair of nodes. Okay. Any pair of nodes. Now we have completed the pipeline, so we can ask why this pipeline is we can use it in the future. If we have a proper representation for the use cases, if we have a parsable representation actually for the use cases, we can have the solution fully automated. By fully automated solution, we can minimize the effort, or we can minimize the human dependence, because the importance of the human here, not to discover a new use case, but to test it only, just to test the availability of this new use case, of this new link, or it's not there. So a third advantage of this pipeline is it's scenario independent. We do not depend on the scenario to predict new links, to predict new relationships. We are just depend on the last use cases, then it can predict new use cases according to the old ones. This all things can minimize the time to implement new use cases and to produce more revenue for all kinds of firms. Let's talk about the results and conclusions. Okay, for the results, we have reached around 86% accuracy prediction in test accuracy. I mean, this accuracy metric is area under the curve, which we have reached 86% here. And we have found that the third scenario representation was the best one in two ways. The first way is it's representable for all kind of use cases, and also it gives us more accuracy than the pure reference code usage. So instead of using only the pure reference code, we can add the node properties, and we will get more results on this. And also we have found that draw.io is the best tool to represent images, or to represent the sequence model that represents all the use cases together. And also we have found that the random forest is the best model to make this prediction. And finally, we have found that by adding more node properties, we can gain more accuracy in our algorithms. Okay, what's our recommendation for better results, or for the next step? We can summarize the first gray points here to have more parsable document. If we have a parsable document, if we have a good parsable document from the old use cases, we can have a better results, and also it can be more automated. This way we can make all the process automated. If we have the old representation represented very well, so we can move on to predict new use cases with very simple steps. And also the next step, okay, here we propose 4 more steps to enhance this work more. First one is to use NLP models to help in this task of parsing documents, or in anything regarding the text manipulation and processing. The second step, we can use other graph algorithms like graph convolutional neural network, which we recommend. And third step, it's to use other ways to represent the graph networks, like network X library in the Python language. Okay. Last step, we can apply node property prediction for not only predicting the relationships or new relationships that's not found before, but also to include or to predict node properties, new node properties for our existing nodes. Okay, that was our presentation, and I'm open to any questions.
Thank you very much for your presentation. Do any other judges have any questions? Okay, everyone, can I thank you?
Again, regarding your presentation, I mean, the framework that you propose, I can say that you have a knowledge base, right? And you are importing and exporting some of the knowledges. Have you ever, I mean, analyzed your framework in terms of the storage or the query or export import capability? I mean, have you ever checked your or try any performance on behalf of that? And have you ever, I mean, do you have any definitions for the, I mean, what kind of protocols will you use to transfer your knowledge in that kind of a framework?
Actually, this problem was mainly built on top of the use cases document. We have a use case document of the autonomous network, and according to this, this is the only resource we have that to know about our current use cases of the autonomous network. So importing and exporting knowledge can be if we have some kind of knowledge base, as you have mentioned, and we can make some protocols between the new predicted and so on. But actually, I think if we predicted new links between any kind of nodes, I think in the first we need to trust in this, because trust in this by letting some experts reviewing this new links, the availability of these new links. Actually, when we predict new links, when we try to predict new links, we predicted around 6,000 new new links between nodes. All these links with a probability more than 99%. This links exists. Okay, and our network was around 300 nodes, I think. So we have 300 nodes presenting or resulting in new or potential around 6,000 links. So we need to make sure that this links is really there or can be found in our real network. After that, we can present it. So if we have this element here can be imported or exported in a proper way, I think we can make this protocol more generic. Did I answer your question or I misunderstood something?
The things that you say is enough for me. Thank you.
Thank you.
Thank you. Are there any other questions from the judges? Okay, well, I'd like to open up the floor to audience members and other competing team members.
Yeah, maybe quick comment, Tarek. Thanks
Okay.
for the nice, thanks for the nice presentation. I think your last slide is most interesting for, I mean, I should say ITU, because I think you have some recommendations. That's quite interesting. And I hope our colleagues actually take note, because you say include sequence diagram representation for all use cases. I mean, that's quite interesting. And also you say parsable way to represent sequence diagrams. That's quite interesting as well. Property prediction. Yeah, I think this is quite linked to everyone's question earlier. The properties representation itself, before you come to prediction, representation itself is quite related to everyone's question earlier. That is that's actually a quite interesting observation that you're making, that property prediction can be used. Yeah, thanks a lot.
Thank you so much, Dr. Bashna, for your mentoring and guidance. Thank you so much.
Okay, thank you very much for your presentation.
Thank you so much for your opportunity, for the opportunity you gave. Thank you for all audience.
Can we have some final words from Thomas or Vishnu?
Well, I think it was quite exciting days today and yesterday, and it's quite good learning for all of us. I believe the teams had good fun, and we hope that you had a good time as well. These solutions don't come every day; they come every once in a year. So yeah, we hope to take it forward. Thanks a lot for coming. It's quite late in many places, and still you are here. Thank you for coming and presenting as well as listening.
Okay, thank you very much. So thank you again, everyone. We do have a survey that is in the chat, so please take time to respond to the survey. The session or this AI in 5G challenge playoff will continue tomorrow as well from 1 o'clock, the same as today. So if you're interested in hearing about other solutions for other problem statements, please join as well. Thank you very much. The session will now be over. Thank you.